Well, so these are the this is the main topic, vector calculus, and under this vector calculus, we'll be discussing with vector valued functions and differentiability
You
concept
are
of
not
it.
audible.
Well, just a minute.
No, sir, it's okay, sir.
It's okay. You are audible, sir.
You are audible, sir.
Yes. So yeah. So am I audible now?
Yes, sir. Yes.
Yes, sir, yes,
So
sir.
you
Yes,
were
sir.
audible
Yes,
even.
sir, you are audible.
Okay. Okay. Thank you. Thank you.
Yes.
Yeah. So these are the topics. Line integral. We will understand what is line integral, surface integral, volume integral, and then we have the important concepts of gradient, curl, divergence. These are all operators, and you will see what are these. Uh, Green's theorem in the plane. So that is the result we will discuss, and then Stokes theorem, Gauss's divergence theorem, and applications means mostly we will solve the problem. And this is the book. So mostly I will for most of the parts I will be teaching. I will use this book, Vector Analysis by Spiegel. Okay, so some of you might be acquainted with this book, and soft copy is available, and you can have a hard copy of this if you can afford. It is a nice book, and especially the problem collection is very good. Okay, so some of you please still unmuted. Yeah, so I'm muting for the time being.
Good morning, sir.
Yeah, good morning.
Sir,
Yeah,
can you
so
repeat the writer of the book?
this is M.R. Spiegel. Let me just write it down. So it is, yeah, too small.
Excuse me, sir.
Yes.
Sir, do we need
Yes.
to purchase this book?
Not necessarily. If you can afford, then fine. It will be a good collection. Otherwise, you can manage with the class notes and other materials which we will provide. Okay, this is not compulsory.
Sir, can you upload it on MS Team?
So this note, lecture note.
Yes, sir.
Yeah,
Yes,
I
sir.
will upload. Yeah, after the class I will upload. So the name of the writer is M.R. Spiegel. S.P. Yeah, is it visible now?
Yes, sir.
Sir, there
Yes,
are
sir.
three types of books it is
Yes, sir.
showing online, sir. Which one? Three books it is showing. Three kind of books. Vector analysis of
Yeah.
Scout's outline.
So vector analysis you can follow. So this one, this book. Okay, so let us go ahead and introduce the concepts one after another. So mostly in this topic, under this topic, we will be dealing with vector valued functions. So what are these? A function whose domain is a subset of r to the power n. I think all of you are acquainted with this r to the power n. So what is r to the power n? So real line is denoted by r. We use the symbol r to denote the real line. The plane is denoted by r square, and the space, three-dimensional space is denoted by r3, so on. Okay, so it is a function whose domain is the subset of r to the power n. It is mathematical language. I will explain what is this. Once I give you the examples, then it will be clear. Some natural number, for some natural number n can be 1, 2, 3. Mostly we'll be dealing with three-dimensional vectors. Okay, and range is a set of vectors. Okay, so every function has a domain of definition and range. Okay, so probably all of you know. So you can think that function is nothing but a kind of machine So through this machine, so what input we take? You take, if n is equal to 1, we are in one dimension, we will take one scalar, say x. And it will process according to the rule of the function, and it will generate some vector, say vx. Okay, instead of scalar, it will just give you a vector. And sometimes these vectors are functions of two variables, say x and y, two scalar variables x and y, and it can be x, y, z, and many more. Okay. So main thing is that input is scalar depending on the dimension of the vector valued function. One scalar, two scalar, or three scalar you have to give as input, and you will get a vector quantity as output. So this is called vector valued function. Mathematically, these are very easy. You can look at the examples. U is the scalar. If you give U, you will get a vector given by cos U I. I is the unit vector along x-axis plus sine square U j plus 2uk. And then next we have discussed one function, vector valued function of two variables. Okay, two scalar variables x, y. We have to give two numbers as input, x and y, and then we'll get a vector in the right hand side. Okay, similarly, three-dimensional vector functions are like this. And once again, we have used another symbol t to denote denote the vector function. So sine 2t I plus cos t j. And then we can have, not necessarily always we have to give a vector in space. We can get a vector in plane as well, or even in a line. So in the fifth example, you can see rxy is equal to, so xij xyi minus x e to the power yj. And then we have this function rxyz. So several kinds of vector valued functions are there. And all of you are acquainted with this type of functions. Okay, in physics and probably in mathematics up to certain extent you have learned all about this. Just we are trying to formalize this idea. Okay, so this is our objective. So vector valued functions probably is clear to you. And then we have the vector valued functions in our head. Different kinds of vector valued functions, function of one scalar variable, two scalar variable, three scalar variable, everything we have. And in that set, we want to introduce the concept of derivative, which is very, very important. Rate of change of something with respect to rate of change of uh, another variable. Okay. If we change one variable, the independent variable, the scalar variable, so how the vector is changing, at what rate the vector is changing, that is our objective to define derivatives. So first of all, we'll deal with ordinary derivative of vectors. Suppose Ru is a vector function of a single scalar variable u. You see, we have a single scalar variable. Then the derivative of r with respect to u is denoted by dr du. So bold r has been used, and if you are writing on paper, you can use the vector symbol like this. Okay, since I'm using the printed material, okay, so I am using the boldface, or in copies, normally you can use this type of symbol. Okay, that is more convenient. You can use the arrow. So R is the vector valued function. So what is this? We define this rate of change of R with respect to U, similar using the similar definition which we have used for scalar functions. So this is precisely the definition of derivative. So you change the independent variable a little bit, so that changes delta u, and you look at the change in the value of the function, which is a vector quantity, and then you subtract the initial value. So ru plus delta u minus ru divided by delta u, and eventually you take the limit. If this limit exists, it is called the derivative of the vector valued function r. So you see the definition is quite similar. Okay, so now let us note that if ru is equal to r1 ui, so these are the components rather. if we write the vector component wise, R1 ui plus R2 uj plus R3 uk. So if we express this vector in terms of its components, it will typically look like this. And then from the original definition, we will see that dr du, d thick r du is equal to dr1 du I, this is the first component, plus dr2 u du j plus dr3 du k. Okay, so therefore, if we differentiate individual components and then we add, we'll get the derivative of the vector valued function. So therefore, nothing is changing, just interpretation is changing. So if we perform the derivative of the components and then we add, we will get the derivative of the vector valued function with respect to a single variable. Okay, so this is about ordinary derivative, and similarly we can define the second order derivative. So after first order differentiation, we are getting another vector, and if we perform the derivative operation once more, we'll get the second order derivative, and so on. We can increase the order of the derivatives. Okay. Next, continuity. The concept of continuity and differentiability is also similar. Okay, so the vector valued function RT is said to be continuous at t. So here it is the function of a single variable t. Can you please mute? Someone is unmuted and talking.
Madhusudan.
Achha, so one thing, can you tell me? I can see very less attendance. So are you informed that today I will take the class?
No, sir, there are 672 students are there.
Yes, sir.
Yes, sir. Almost in every class they are same only. Means in every maths class, almost
Yes,
same
sir,
only.
generally same only.
So how many of
So
you
there
are
are 675
present at this
attendees.
moment?
670, sir.
680.
680.
687, sir.
My laptop.
Okay, fine, then fine. Okay, so let me continue. Thank you. Yeah, so the concept of continuity and differentiability, that is also similar. Okay, similar to the corresponding concepts of continuity and differentiability in case of scalar functions. Okay, where vector is not there, we have scalar functions, and we understand what do we mean by continuity of a function and differentiability of a function. Okay, so in this case, if the components are continuous, then the vector, so let us suppose the vector RT, thick RT has components R1T, R2T and R3T, and if the components are continuous, and we understand what is the meaning of continuity of a scalar function. So these components are scalar functions. Okay, if these three are continuous, then the vector valued function is also continuous. And it is said to be differentiable if differentiable of order n if its nth derivative exists. And we have interesting result, another interesting result. A differentiable function is necessarily continuous. Achha, if a function is differentiable, okay, if a function is differentiable, then it is necessarily continuous. We already acquainted with the result, and we have the famous example of the function fx is equal to mod x, and at x equal to 0. So the converse is not true. At x equal to 0, the function is not differentiable, left hand limit,
But continuous.
but continuous.
Continuous, sir.
Yeah. So same result is will hold in this case, but we will not emphasize these aspects, these theoretical aspects of the problem. We will consider the vector functions and we will do different kinds of operations. Okay, we'll not too much stress on the on these aspects, this limit, continuity, differentiability, etc. Okay, we'll consider normally the functions which are sufficiently smooth. That means we can differentiate any number of times as per the requirement, and all the functions that will appear in our discussion will be mostly continuous. And if there is any change, okay, if we are considering any special kind of function having different kinds of discontinuity and uh, different kinds of problems at different points, then I will discuss it specially. Okay, otherwise we'll consider with very nice behaved functions. And these are some of the natural rules, probably you have been using for long, but still I have listed it for our convenience, for our discussion. Okay, so if we differentiate, suppose A, B are two functions of a single variable t, vector valued functions, and psi is a scalar function. Then these rules we can use if necessary. ddt of A plus B, sum of the vectors is equal to dAdt plus dBdt. That means you differentiate individual functions and then add. And if we need to calculate the time derivative of the dot product of the vectors A and B, vector valued functions A and B, then we have the similar kind of rule. You see, product rule we have been using for scalar functions. A dot, only thing is that we have to consider this operation dot product, and a similar rule is valid for cross product as well. Note that in the third formula, order we cannot change. Okay, if you change the order, then it will not be valid. But in case of second formula, you can change the order because dot product is commutative in nature. A dot B is equal to B dot A. There is no problem. But in case of this third rule, you cannot change the order. Then you have to take care the sign contribution that appears in a dot product. And if we multiply a vector function A with a scalar function, eventually you will get a vector. And then what we can do, how we can evaluate this, this is the formula, psi dA dt, this is the vector differentiation, and then d psi dt is the scalar differentiation and multiplied by a vector, and in the right hand side we'll get a vector. So these are natural rules that will directly follow from the
Excuse me, sir. Excuse me, sir.
yes, yes, yes,
Sir,
please.
sir, can you give the example of the fourth part,
Yeah, yes, yeah.
d of psi a by dt?
Okay, so suppose you have why it is not right. Yeah, so you can take psi, say t is equal to, let us take very simple thing, and a is equal to say ti plus 2t squared j plus say t cube k is the vector function. And then psi a, this is basically equal to, if you differentiate this, so how we will do, t square fixed, then dA, sorry, not del, dA dt plus a fixed, here you can, okay, just,
2t,
yeah,
2t psi
2t,
t by dt.
2t,
Psi t by dt.
yes, no, d psi dt is equal to 2t, and then you have to write this a. Okay, so this is how you have to, you can operate. Otherwise, you can just multiply the scalar function component wise. You will get tqi plus 2t to the power 4j plus t to the power 5k, and then you can differentiate. Okay, is it all right, or
All right.
Yes, sir. Yes.
okay? Okay, so let me just introduce the partial derivative. In case
Sir,
of
one thing.
partial,
Sir, in the
yes,
fourth formula, it is only the simple multiplication, scalar multiplication, which we have done now.
yeah,
So
yeah,
if we
simple
write a
multiplication.
d psi by dt, it will not affect now. In
No,
the
this
fourth
I
formula.
d by dt will be a scalar function, and you have to multiply this scalar function to this vector a.
Sir, both the psi and a function should be in the form of t.
Yeah, so we were dealing with a function of single scalar variable t.
Okay, sir.
Okay. So it will come naturally actually. And then if v, the vector valued function, is a function of two variables, say x and y, instead of t or u, you have two variables x and u, y. Then naturally there will be partial derivatives. Okay, if we want to define the partial derivative of v with respect to x, then this is the definition. First one, del v del x is equal to limit delta x tends to 0 v x plus, we are changing the x variable little bit and looking at the change in v, in the vector v, x plus delta x y minus v x y by delta x. Probably you have learned this in your class in function of several variables. Okay, so partial derivatives have been defined there. But yeah, nevertheless, I have kept this definition for you. So del v del x is equal to limit delta x tends to 0 v, x will only change, comma y will not change, will keep y, minus vxy by delta x. If this limit exists, it is called, at the point xy, it is called the partial derivative of v with respect to x at the point xy. And if we are interested to find the partial derivative at a particular point, say ab, then we have to put x is equal to a and y is equal to b. That's it. Similarly, we can define del v del y. And in this case, we will change the second variable, not the first one. First one will remain fixed. So Vx remains fixed, y is changing, y plus delta y minus Vxy divided by delta y. Limit delta y tends to 0, so that we can move to that point xy. And if this limit exists, it is called the partial derivative of the vector function v with respect to y. And the idea of continuity and differentiability is directly connected with the idea of continuity and differentiability of the function of several variables. Okay, so there we have introduced the concept of the continuity and differentiability of the function of several variables, and we will once again not go into the theoretical details, theoretical aspects of the concept of continuity and differentiability. And we would assume that all of us have some idea or some intuitive idea of the concept of continuity and differentiability. Differentiability is very simple, because if we can differentiate, and then it is called differentiable at a particular point. And if we cannot differentiate it at a particular point, if the derivative, this limit does not exist, then we will say that it is not differentiable. Okay, something like that. And similarly, we can define the higher order derivatives. For example, del v del x, if we look at this, it is a vector in the right hand side, and it is a function of xy. And once again, if we what we can do, we can differentiate it with respect to x or with respect to y. Okay, while differentiating with respect to x, we will consider y to be constant, and on the other hand, while differentiating with respect to y, we will consider x to be constant. So that is the operational procedure, and these are the theoretical definitions. And here I have listed two important formula. Del del x, partial derivative of the scalar a dot b, scalar product of a dot b with respect to x, is given by this formula. Okay, a dot del b del x plus del a del x dot b. And similarly for cross product, we have this formula, and similar kind of formula we can derive for del del y. So while differentiating with respect to y, and if we consider the other higher order derivatives, so this formula can be repetitively used. Well, so here I have kept some of the exercise problems. You can consider this. So I will show you some of the solutions. So R, this e to the power ti plus ln t square plus, okay, R is equal to this vector is equal to e to the power minus ti.
I have a question.
Yes, just
So
tell me.
when we talk about
Yes, please.
when we talk about differentiability, both
Mhm.
the partial derivative must exist. Or if one of the partial derivative does not exist, then it is not differentiable.
We will consider, we'll just say that it is differentiable with respect to x only. And if both the different partial derivatives exist, and we will say that this is differentiable.
Okay, sir.
ln t
Okay,
square
sir.
plus 1j plus ln t square plus 1j, and what is the third component? Third component is minus tan tk, minus tan tk. So then dr dt is very
Minus
simple,
t की power
minus into minus ti
plus 2t upon t
plus 2t upon t square plus 1
minus
j,
t.
sec square t k.
ठीक है.
Yeah, and we can this is you see, this is a vector second order derivative. We can once again find easily e to the power minus ti, and this is not so simple. I leave it to you.
Division.
Yeah, so, and this is also 2 sec t and then sec t tan t, so sec square t tan t k. And this derivative, if you can calculate, you will find the result. And once again, we can find the modulus of it very easily. So it will be basically e to the power minus 2t plus ln t square plus 1 whole square. No,
Is it
so I have to,
2t square plus
4t
1
square,
square?
4t square 1 plus t square whole square plus sec 4t. And if it is asked to find the magnitude of this vector at a particular value of t, then you can easily find it out. So working rule is very simple. So I have listed some of the examples. I think you can try it. I will provide you this and you can try it. A cross B cross product you can find. If A and B are given, then you can find the cross product. You will get another vector. So this is the, I'm talking about the exercise problem 5. So A cross B, you will get a vector, and then so del square del x del y means del square del x del y means
And order derivative.
this is higher order derivative del x del y on something say f. So what you have to do, this is basically del x del f del y. Okay, so first you will perform the derivative with respect to y, and you will get another vector, and then you have to perform the differentiation with respect to x. You will get eventually get a vector. Okay, so you can just try these simple examples, and you will be able to understand what is happening and how to work with these vectors.
The previous example.
Huh? Please.
The last one, please solve.
Which
Before
one?
this one. Yeah, where you
Sir,
solve this
Last one.
first number example. Example 1 you solve, no sir, that one.
This one?
No. Where you solve that example 1.
Oh, this one?
Yes, this one. Okay. Thank you, sir. Done.
Sir, we can find cross product, then we can differentiate.
Yes.
sir.
Yeah.
Okay.
Oh.
Yeah,
Sir,
you
please
have
show
to, first of
last.
all, you have to find.
Sir, please
So
show
first
the
we can
procedure
find
of
A
last
cross
one.
B.
No, one by one, please. I need to. So which one? This example? This
Yes,
one?
sir, please.
I need to show this?
Yes, sir, please.
No, sir. Only say the procedure, sir. How to do? We will do ourselves.
Okay, so A is equal to x square yz I. I have two vectors. A x square yz I, x square yz I, minus twice x z cube, minus twice x z cube, twice x z cube j plus something is there,
XZ square, sir.
x z square. Okay, and B, can you tell me or should I?
2z I cap.
Eh?
2z I cap plus yj cap minus x square k cap.
Yes, sir.
J minus x square.
K cap. Yes, sir.
Okay, so
Sir,
then you
Y J
first
cap, sir. Z not, sir. Y J
y
cap.
only y.
Yj cap only.
Yes, sir.
Okay, so A cross B you find first. I j k, so x square yz minus twice x z cube x z square twice z plus this is y and then minus x square. So I into this 2x cube y z cube minus
Minus XYZ square.
x y z square. This
Z
is the
square.
first component, and then j into 2x z
Minus
cube plus x to the power 4 yz
YZ.
plus k into x square y square z plus 4 x z to the power 4. Okay, so this is my vector. Now I will just, so what I need to do, find
Sir, instead of finding the A cross B at first, can we apply the double differentiation for the A cross B, that method, twice?
yeah, you can do that. That is another possibility, but
Okay, sir.
note
Okay,
that
sir.
first of all you have to find the derivative with respect to y, and then whatever
Right.
you will get on that
With
function
respect
once
to
again,
X.
yeah, with respect to x. Okay,
Okay,
so
sir.
I
Thank you.
think you can manage now with this vector.
yes, sir.
Yes, sir.
Okay, so let me now introduce the concept of scalar field and level surfaces. Okay, so what are scalar field? Have you ever heard about this term, scalar
No,
field,
sir.
vector field?
No, sir.
No, sir.
Okay, okay, so let me give you, so unknowingly you have been using different scalar fields. For example, you talk about the gravitational potential due to earth. Okay, so earth's gravity, due to earth's gravity, so we use this term gravitational potential. And pressure field, sometimes we suppose in this room, in a particular room, if you measure the pressure at each and every point, then you will get a scalar field. Potential, if you measure the potential, gravitational potential, or potential due to some magnet or due to some charge placed at some point in the room, so you will then what you will get, basically you will get some number. You will be able to assign unique number at each and every point in the space or in this room. Okay, so then what is the scalar field? The region in which the function is defined together with the function is called the scalar field. Okay, formally how one can define? Suppose at each point P, x, y, z of a region R of space, you take some region of space, and at each point, suppose a scalar function is uniquely defined. This is very important. Uniquely defined. There cannot be more than one value under this discussion. Uniquely defined, then the region R together with the function is said to form a scalar field. Field means some region actually. Okay, in this is not an ordinary region. In that region, a special function, scalar function is defined. Okay, it may be pressure, it may be potential, okay, it may be density of some fluid in this room. So several kinds of scalar quantities one can assign uniquely at each points in the region of space. Then what will happen? You have a region, and in that region at each and every point you have some functional value. Okay, it may be related with the physical quantity of pressure, it may be related with the physical quantity of potential, okay, something like that. And temperature, if we measure the temperature at each and every point in a room, then we have a region which is the space occupied by this room, and with this function, temperature function, for example, temperature function or density function, okay, this region with this density function or temperature function or any other scalar function, this region is said to form a scalar field. Okay, so in this scalar field, once we have a scalar field, mathematically it is nothing but a function of some scalar variables. Okay, scalar field is nothing but a function of scalar variable, and which is defined in a particular region. It has its domain of definition, so therefore it is basically a function. Now, what are iso-phi surfaces or level surfaces? If phi is equal to constant, okay, for example, we have been talking about iso-phi surfaces, isopotential surfaces. Okay, so these are basically surfaces within that region where the scalar field or scalar function is defined, where the value of the function is constant. Okay, for example, it will be clear to you if we consider the function this y square plus z square. Okay, if we consider this function and assume that this defines a scalar field in the three-dimensional space, then what are the level surfaces? These are the level surfaces which are obtained by equating this with a constant. For example, if you take c is equal to 1, what we will get? We will get the unit sphere. Unit sphere. So on each point on the sphere, the value of this function is 1.
Then it will be isosurface.
Then it is one isosurface. Now if you change the value of the constant, say 2, you will get another isosurface or level surface. If you change it to say 5, you will get another isosurface. Note that no two level surfaces can intersect. Okay, if two level surfaces intersect, then what will happen? Two different level surfaces intersect.
They cannot
Different values, sir.
Sir, it will
at
not
the
be
same
uniquely
point.
defined.
At the same point, there will be
because
two
there are
Yes,
content.
let me
a
explain. Probably all of you, or most of you understood. So if there is some point of intersection of two different level surfaces, then how the definition will be violated? For example, let us suppose this is the point of intersection, and we know that value of phi on this level surface is C1, and on this level surfaces phi is equal to C2. Okay, but at this point phi can have either the value C1 or it can also have the value C2. But it is not allowed by the definition. You see, phi has to be defined at each and every point in the domain of definition uniquely. So that uniqueness is violated. So therefore, from this important word, okay, insertion of this important word uniquely in the definition, the intersection of two level surfaces is ruled out. So therefore, two level surfaces can never intersect. Okay, so this is an important point we have to remember. Then we have the concept of vector field
Sir?
in the, it is defined, yeah, yes,
Sir, equipotential surface can be called as a level surface.
yes, that is associated with that potential function. Function is changing. Okay, if you change the function, then you will get different level surfaces. In general, we use the term level surfaces, but if you consider the potential function, so later you will see different kinds of potential functions will appear in different problems. At this moment, mostly you are acquainted with gravitational potential functions. Okay, if the height you take, you are in the same height from the sea level, approximately from the sea level, then at each and every point the value of the gravitational potential is same. So therefore these are basically horizontal planes. Equipotential surfaces in that case are horizontal planes, and if you are looking at the level surfaces from a very distant location, then it will have some curvature. Okay, if you look at it locally, you will see that these are horizontal, but if you look at it from a distant object or distant reference frame, you will see they have some curvature, sphere like structure around the earth surface. Okay, so this is fine. Well, so vector field, what is the vector field? This is basically a region of space, and in that region what is defined, at each and every point a vector function is defined uniquely, once again uniquely defined. Then that region is said to form a vector field using this function f, vector function f. In the scalar field, scalar function is involved, and in the vector field, vector function is involved. And what are the examples? Velocity of air in a hall at
Electric
each and
field.
yes, please repeat.
The electric field, right?
Yeah, electric field. Yeah,
Acceleration due to gravity.
yeah, acceleration due to gravity. That is also a vector field. And gravitational force. Oh, that is a typo. Not gravitational force due to Earth. You take a smaller object near to the Earth's surface, and then at each and every point you assign the gravitational force due to Earth, then you will get a vector field. Okay, velocity field, acceleration field. Okay, later you will understand vorticity field. Vorticity is normally used for
Fluid mechanics.
in fluid mechanics. Yeah, this is basically Carl operation. I will discuss later on. So at this moment we cannot take this example. Force field.
Yes.
Yeah, force, velocity, acceleration. Yeah, so these are the frequently encountered vector fields. Okay, so essentially what is the concept? We have a region in space, we have some region of space, and there at each and every point a vector is uniquely defined. Okay, so that is the vector field. Well, so now the very important concept of vector gradient. Vector gradient. So what is the starting point? At the starting point, we have to consider a scalar field. We have to consider a region of space where a scalar function is defined. You can take the example of temperature field. At each and every point, we have some region of space, and at each and every point, the temperature function, temperature is well defined, uniquely defined. Okay, so you can freeze your time if you like. If it is unsteady, the temperature distribution is unsteady, that means changing with time, then you can freeze your time. You can take a snapshot. That means T is equal to T0. Then if you consider the region which is confined within your room, then at each and every point you will have unique temperature at a particular time. In the next time it may change, but we are not talking about that. So we are just considering this is basically stationary kind of behavior. Okay, at each time we have unique temperature. We can assign unique temperature at each and every point in a particular room. So that will define a scalar field. And you can consider the gravitational potential or potential um, due to some potential due to some electric field. or due to some magnetic field. So you can basically consider a scalar function which is defined in a particular region of space. That is the starting point. And we call that scalar function, scalar field, as, or denote that scalar field as phi. Okay, so within that scalar field, you take a point P. You take a point P, whose position vector is R with respect to some reference point O. The position vector of P is R, thick R rather, or R vector you can imagine, with respect to some reference point or reference origin O. And through this point P, a level surface will pass, defined by this scalar function. And let us suppose the value of this value of phi on the level surface at each and every point on the level surface is phi. And then you consider another point, nearby point. Note that this is very close. In picture we have shown it at a finite distance, but normally this is very close for the theoretical aspect or theoretical concept. This P dash is a nearby point. Okay, so then this P dash vector is delta R vector. Delta R vector. And this delta R vector is equal to, its magnitude is taken to be equal to delta S, and A cap is the unit vector in this direction, PP dash. So this PP dash vector is denoted by delta R vector. A is the unit vector in the direction PP dash. A cap basically. So this is A cap. Unit vector, I always consistently use this cap symbol to denote the unit vector.
Delta S.
This is delta R.
Magnitude.
This is equal to delta S A vector. Okay, A unit vector along this PP dash, and delta S is the magnitude of this delta R vector. These are all small quantities, therefore this delta symbol is used. Okay, so P is a point whose position vector is R, and P dash is a point whose position vector is P dash is equal to R plus delta R basically. Therefore PP dash, you see, this becomes delta R vector whose magnitude is taken to be delta S, and unit vector along PP dash is taken to be A cap. Okay, so up to this it is fine. And then through this point P dash, another level surface will pass which will not intersect the first one which was passing through P. And let us suppose the value of phi on that level surface is phi plus delta phi. So some change. So in the first level surface, value of the scalar function is phi, and in the second surface its value is phi plus delta phi. And now let us draw a normal from the point P to the surface S dash. Let us call this first surface as S and the second surface as S dash, level surface. And you draw a normal at this point P to the level surface S dash. This angle is 90 degree. Okay, so this angle is 90 degree. Now the magnitude of PM is delta N. PM, this vector magnitude is equal to delta N. N stands for normal direction actually. Okay, and unit vector along this PM is N cap. So this is my configuration. So unit vector along the normal direction is N cap, and unit vector along the PP dash direction is A cap. And this angle is assumed to be equal to theta. Okay, so this angle is assumed to be equal to theta. Now,
So theta will be very small.
Yeah, it can be. Yeah, it is normally small. You see, P dash is nearby point, and if you take your P dash somewhere here, it can maximum go up to around 90 degree actually.
Sir, sin theta will be delta n by. So cos theta will be delta nn by delta s.
Yeah, so I am coming to that point. Yeah, so another question was there. So yeah, what is that?
So theta
Sir,
can be
sir,
bigger
here
also.
each
Yeah,
eye
it
is
can be finite actually. Not necessarily it should be very small, because you can
Yes,
take
sir.
a nearby point somewhere here. In that case, it can be 90 degree, around 90 degree actually, close to 90 degree. Okay.
Sir, you are
Yes.
mentioning GP dash vector. What is G there?
G. G is not. I don't find any G. Are you talking about this one?
Sir, GP dash vector
OP
equals to
dash.
R
It's
vector
OP
plus
dash,
delta
OP
R
dash.
vector.
OP dash. Oh,
OP
acha,
dash,
acha.
bro,
So
it's OP
my
dash.
excuse me for my handwriting. OP dash. That is OP dash. This one. I think you are talking about OP dash. OP dash is it is a
Okay, sir.
R plus delta R. This.
sir. From this observation, can we give the relation between the constant values also C1 and C2?
C1 is phi actually. I have taken, and C2. C1, C2. What do you mean by C1, C2? Means values of the constant on the level surfaces. Is it your point?
Yes, yes, sir.
So we have taken phi, value phi on the first level surface, and the second level surface, which is slightly away from the first one, we have taken the value of phi, a value of the function constant to be equal to phi plus delta phi. Okay, we are basically, our objective is to basically measure the rate of change of phi. Okay, rate of change of phi, how phi is changing. Value of this function is changing as we are moving from one level surface to another level surface in a particular direction. That is our objective. So yeah, so we have discussed the initial configuration. Then what we will do, yeah, so I have mentioned the position vectors and pp dash, as I already mentioned, that this is delta r, and delta, which is equal to delta s a cap, and delta s is equal to absolute value or magnitude of this delta r vector, and pm. Up to this we have done. And now what is your uh, uh, delta n by delta s? You look at this triangle now. You consider this triangle. So from this triangle, what we can get?
Cos theta, sir.
Cos
Delta.
theta, sir.
So this is 90 degree and this one is theta. So delta s by delta n. This is hypotenuse by base.
Cos theta.
Sec theta.
This is sec theta. So
Sec theta, sir.
then let us
Oh, yes,
use
sec theta.
delta n by delta
That
s.
is your point.
Delta n by delta s. So normal by hypotenuse, yeah, base by hypotenuse, that is equal to cos
Cos
theta.
theta.
Note that these delta, they are small quantities. They are not differentials. They are small quantities. This is cos theta. Now,
Sir, here delta n and delta s are vectors.
no,
So
I am
delta
talking.
S,
Delta s is not vector, you see. This is scalar.
Okay, sir.
This is the absolute value of this delta r vector. And delta n is the
yes, sir.
absolute value of this delta n vector. Okay, delta n, yeah. This is basically delta n cap, and this is equal to delta n vector, and absolute value of this delta n vector, which is the vector pm, is equal to delta n. This is the magnitude. Okay, we are not,
Sir,
yes.
sir, how can we sure that P dash and M are right angle triangle?
So we have drawn, this is by construction, we have drawn the normal from P to the level surface, and it has intersected the level surface through S dash at M dash, AM. So therefore
Sir,
this
we
is,
have drawn on the level surface, na?
so
Sir,
we have
P
two
dash M is
adjoining
curve,
level
na?
surfaces. We have two
Sir,
adjoining level
sir,
surfaces like this. Yeah,
curve
please.
can
Sir,
be
P dash M is
maybe
curve or
in a
straight
curve.
line.
Yes, a straight.
No,
It is a straight line.
P dash.
P dash time is a straight line.
please let me answer the first question. So you have two level surfaces like this. They cannot intersect. If you locally look at those level surfaces, you will see that they are parallel to each other. Okay, and then it is not difficult to imagine that you can draw a perpendicular from the point P to the other level surface. Okay, they are very close to each other, and locally they are parallel to each other. Otherwise, they will intersect, and intersection is not allowed. Okay, so therefore, it is difficult. It is not difficult. For example, you can consider two concentric spheres of different radii. Okay,
Yeah,
and
yes, sir.
you can take a point P on the inner surface, and then you can draw a normal to the outer surface. So this is by construction.
Sir, I'm talking
Sir,
about
AKF
the
is the unit
P dash
vector.
M.
Hmm?
Sir, I'm talking about P dash M and P. Means it is not sure that it will always make 90 degrees.
P dash MP locally. So P dash is very close actually.
Oh,
Acha,
P dash is very close,
acha,
sir.
yeah, P dash is close to P. Yeah. Delta R. Otherwise, yeah, you were right. There may be different curvature. Okay, so that is your point, right?
Sir, P dash M is not used in anywhere, so it's not matter whether it is curved or straight.
No, please, what is your point? Yeah, please repeat.
Sir, P dash M is not used anywhere right now, so it doesn't matter whether it is curved or straight.
We are taking
Basically,
triangles. That's why we are
we will
taking cos
consider the
theta.
triangle. Na? This is, we will consider the
Sir,
triangle.
it will be curved because theta is not infinitely small. Theta has a finite value. So delta
Yeah, so
N into
therefore
theta.
it turns out that P dash we have to take close to this
Delta N into theta.
yeah, theta we cannot allow very large actually.
Sir, it would not matter for theta. We could just join P dash and M by a straight line. It would not matter.
No. So
P dash और M को एक straight line
But
से
after
जोड़ लेते
that, it will not be right angle triangle, na? It will
हाँ,
join
एक
that.
right angle
But
बना
then the
के
curve would not be included in the triangle
just
part.
very
So
far away from M and theta.
yes.
If you allow large values of theta, which I initially mentioned, I think we need to correct that thing. So thank you for the question. So we cannot allow very large values of theta. Then this right angle approximation will be violated. You cannot have this right angle. Suppose you have this kind of thing. This kind of thing. Local curvature is this kind of thing. Then what will happen? So
P dash will be on the S dash though.
yeah, so S dash, suppose S dash is moving like this, curvature is larger.
But then S and S dash will intersect.
Yes, sir. Then S and S will intersect.
No. Sir said that both the curvature will have
both
this
the
type of curve.
both
Means
the curves same.
yes.
Same
No,
as
if you allow
tilted by
theta to be very large, then there might be some problem.
Sir,
With
we
this,
have
with this
Yes,
right
sir.
angle approximation. I am convinced with this point.
Yes.
Sir, what is the problem?
Sir, please kindly bind this class, sir. We have our next class from 10.
Oh, so what is the time now?
10:05, sir.
Sir, already 10.
Sir, it's already 10.
Yes, sir. It's already
Okay, so then I need one extra class. When can I take schedule on this topic?
Sir, tomorrow?
Tomorrow Wednesday time 9 o'clock.
Tomorrow 9 a.m.
Yes, sir.
Morning, sir.
Yes, sir. Tomorrow morning.
Tomorrow 9 o'clock is fine for you.
Yes, sir.
Okay, sir. Okay, sir.
Yes, sir. Yes, sir. Tomorrow
Okay,
9.
so
That
then
will be good for our extra
Sir,
class.
we'll
tomorrow
continue this
is
discussion.
mathematics class only, sir. Tomorrow morning is mathematics class only.
So tomorrow 9
Late
o'clock
tomorrow.
we have maths class.
No, that will be taken by other teachers. So on different topic, I will. So I need. Do you have some empty slot in the morning?
No, sir, we have no.
So then
It is
before 9 a.m. Take tomorrow math class, sir.
You can take
No,
out
tomorrow
Sunday,
math
sir.
class will be taken by other teacher. So
Yes, sir.
if I take the class on Saturday,
before 9 a.m.
difficult for Saturday?
Yes, sir. Saturday is okay.
Saturday or Sunday.
Okay, sir. Okay, sir.
Saturday after 10 a.m.
Sir, you can.
No, no, not after 10.
No, sir.
After 11.
No,
Because
sir,
after
on
from
Saturday
10 we
we
have
have
class.
workshop on that day, sir.
Sir,
You have workshop.
Sir, is it possible to take the class on Thursday?
Thursday,
Thursday
I have,
afternoon.
Thursday afternoon, sir?
Today 2 o'clock, sir.
today you can
2
leave.
o'clock.
So same day 2 classes.
Thursday
Can
is
we
okay,
Sir,
leave, sir?
actually, sir, this is
Can
class
we
for
leave,
the
sir?
section A to J, sir. So
Thursday is okay,
there
sir.
are many
Thursday
each
afternoon.
and every.
Okay.
Sir, by this it is
Can
not
we leave,
possible.
sir?
Our last class is finished,
30th
sir.
February.
Like
Saturday, sir.
sir, whenever
Sunday.
you
Sunday evening.
Sir, tomorrow 8 a.m.
Sunday evening.
not tomorrow, Thursday is okay, sir.
Sir, tomorrow
Sir,
8
can we
a.m.
leave, sir?
Sir, tomorrow 8 a.m.
No, sir, tomorrow 8 a.m.
Take our attendance.
Sir, any day evening or
Sir, not at 8 a.m.
Yes,
sir.
sir. Any day
Sir,
evening.
take the attendance.
Wake up
No,
at 8
sir,
a.m.
no,
Take
sir.
the
We have
attendance,
yoga,
sir.
sir. Sir, we have yoga
Guys,
class,
please
sir.
be quiet
Thursday is
now.
okay, sir. Thursday.
Sir, we
Hello.
can't.
Sir, hello.
Now we don't have any
Hello,
class
sir.
because our EVS
Hello.
class is cancelled.
So
Stop the
Thursday you don't
recording.
have class. Thursday